record on this computer. Yeah, that's good. Yeah. Okay, let's continue that what we had been doing last time, that we were just going through this assignment. I think we were talking about this one, the multiple regression. Because this time we had another regression, see, not one variable, several variables being taken into account. So we kind of talk about this one. Hey Magnus, good evening. You didn't miss anything. I just started, okay?
All right.
Just started, okay? So now I got back to that the assignment that I have been doing that last time, okay?
Okay.
Okay, so that question number one we talk about this one very elaboratively last time. Can you remember? We talk about this one interpretation, same like in that the other assignment. We had an interpretation for the correlation between if it is a two quantitative, means here like let's say the chance of admit versus research experience. So this one is always like a quantitative, the quantitative. So but research, if you add the research as a x variable, this is the y variable, only this part. If you're gonna Hey Benjamin, good evening. You didn't miss anything, okay? I just started. I got back to that our assignment that we had been doing, okay? So that last time that I'm talking about here, that how to make the interpretation like in the other assignments, quantitative variable, two quantitative and one quantitative and a categorical. Here chance versus research experience, if you like get the correlation, it's not related to this whole thing being taken into account at the same time. See? Chance versus all these. No, this one chance versus uh, this one. Should be actually that come with like a subscript. That's okay. You know what that means. Yeah, research versus chance of admin. So this is categorical versus quantitative. So your uh, explanation or the interpretation or the definition should be written in this format. Okay. The undergraduate versus this one. Then quantitative to quantitative. Letter of recommendation. I mentioned about these two. You can either consider like a categorical or quantitative. We had that broader discussion the last time. Either way is fine. Okay, and then put the values over here. Interpret any way you want, or if you want to interpret both ways, that's fine too. See? So we are leaving more space for you to that do this one any way you want. I mean, like when you see that this can be done in several ways, that's the best way to get things done, because not only in one way. Okay, these are for the B's, and then it comes to the point that we notice that there are several confidence intervals. So we restricted our discussion only to the betas. Betas means this guy's confidence interval, not the R's confidence interval. We saw the R confidence interval as well, but they were not the one that they were expecting. Okay, so it's kind of like a same thing, like a parameter when you run the supernova for the pre-F and P value. Yeah, see correlation interpretations, regression weights for the B naught and B naught and not the B1. It should be BI, because it's going to change from that regressive variable to regressive variable. Okay. Anyhow, they were assuming that the B1 means like a one at a time, B1. Okay. If you run that explanatory variable, this one versus the other one. Oh no, this one for the multiple regression. I'm sorry. This one. This is for correlation, model parameters. Yeah, supernova interpretation. This is for the multiple regression, not the single one. You have to make sure that you're on the right track. These ones, all these one for the multiple regression. Pre for the model, F for the model, degrees of freedom for the model, model F, it has a two of them, and a p-value for the model, b naught for the model. But here, these one for when you do linear regression. These are for the linear regression. This is related to get correlation and p-value between terms of admittance and value. Put those values in the table below label. Then perform multiple regression analysis, the outcome variable chance of that, and fill in the rest of the table. That means this part should be filled in with the aid of multiple regression. This part with the aid of univariate or simple linear regression. Simple, this one, multiple. Okay. Then for the go down, these are multiple pre F p value. Model parameters. Model means like parameters related to this one. So when you are running this one, you saw that when it comes to my mind that something came to my head, something came to my head when I was looking at this one, because that this one even get it done when we're talking about the regression things that you're going to take more classes down the road. The same thing can be get it done in several ways. The regression is one of the approaches. You can go to regression, or you can go to time series, or you can go to the decision tree, or you can go to the neural networks. That's how these are pretty much the same thing being approached in different methods. So we are just be simply learning the regression only. Down the road, you're gonna learn the time series in like a 400, 620 class, right? Time series. Later on, you're gonna learn about the decision trees. Later on, you're gonna learn about the neural networks. So this all pretty much gonna utilize in order to tackle something like this. Classification and regression mainly. You see? Okay, that's something I'm gonna remind you over here. That's why I started writing some program for that one. See, this is the same kind of a regression. See, it's a regression when they were Boston housing value in the suburban of Boston. See how their price would be based on that these factors, like a multiple regression. See, these are multiple, but we don't tackle that one multiple regression. We're gonna tackle that one using neural networks. So anyhow, I get this one. Okay, we talk about this one. I think Mr. Jeff. That's okay. Mosaic, I don't mean Mosaic already running, I think. Yeah. So this one a little bit. It's this one. Factor level 6 research F, that's good. And then see, these are the correlations. All correlations we got, they have their confidence interval as well. We talk about the T, D, F, P value in a large scale. See, pretty much for all these. Multiple regression we talk about in a several ways. Then now we get into the multiple linear regression. Supernova cannot found. Type 1, type 2, type 3, we talk about that one in board range. You know that one. There are differences, everything in a large scale we talk about. There are even calculations over here. You don't have to reproduce that one for your that assignment. You don't have to. Then there's no to. Then we did the centering. When we saw the negative value for the intercept, we got rid of that one by subtracting that your data by subtracting certain value from that one, either that this is a center or just some value close to the center. Okay. We got it done in 2 ways. Okay. Then the new intercept is nothing but based on this formula. We got that one. Interpretation, Q2, all the interpretation, as I said earlier, pre. Let's see the pre. This the pre they're talking about. Multiple, okay? I'm talking about, that's what I want to make sure that this part here. This part you can fill in, okay? This one we can fill in too. Pre-model F here, P-model B naught, all are here. B naught. Either you can put with the without centering or with centering. That doesn't matter. I mean, like I showed you that if you feel somebody gonna question you and ask why we have a negative, that doesn't make any sense. Anyway, that we can get rid of that one. That's the part I showed you the technique, the centering. So anyhow, this, if you want, you can put this one without centering B naught, and then B1, B2, B3, and like that. They are corresponding confidence intervals. See, to fill in this here. Okay, this one R separately we calculate earlier, and this one for the multiple regression. That means it should be taken from here. See, model 1. Normally, when you run this ANOVA, you get the model 1. Can you remember? But when you run supernova, you get model 3, the type 3. So, but the value on the top not gonna change. These are the values gonna go to go over here. When it comes to the degrees of freedom for the model, there are two. They were talking about that 2 means, as I mentioned earlier, 1 degrees of freedom for this guy, which is 4 for F divided by the error degrees of freedom, which is 395. Okay, that's what I meant. 4, 395. Okay. 395 there, then it's done. Okay, then that part we not over there. Then we come to pre-F and P value. The pre-F and P value. Pre based on this pre 7870. See how much being explained by it. See 78% of the variation chance of admittance is explained by research, not only research, LOR, SOP, and GPA. The 78% of unexplained leftover error from the empty model has been explained by the multiple regression model. If the MS explained by the model per additional parameter is 364, this one, 0.798 times larger compared to the variance unexplained in MS. See? The ratio of explained error by the model per degrees of freedom to unexplained error by the model per degrees of freedom. Explained error, see? This is called the explained error per degrees of freedom divided by unexplained error per degrees of freedom is this much. That ratio is called the F p-value. The probability that the F values are extreme than the observed F value. P-value. What do you mean by p-value this month? See this p-value. This p-value related to which one? That's why we have now very confusing, because this is a random variable too. See, now at this stage, okay, SS, can that be a random variable? Yes, not degrees of freedom. MS, can that be a random variable? Yes. F, can that be random variable? Yes. Pre, can that be random variable? Yes. Then this F related to what at this stage? It's related to not to pre, it's related to F. Okay. So the probability that F values are extreme than the observed F value, which is F naught. This is for the F ratio test, which is an overall test of an all parameters. Another way, We reject the null that the model parameters are all equal to 0 and infer that at least one of the parameters not equal to 0. That is at least one of the regressor variables. Explain the variation of chance of admit. What that means, what we are trying to say over here. They say that so many things we're going to talk about that for this p-value. See? Even for this one. This one for sure that as I showed you last time, see, this is in multiple regression, okay? We are in multiple regression, multiple one. So in multiple one, sum of squared regression divided by degrees of freedom is MSR. MSE is SSO degrees divided by degrees of freedom for error. Their ratio again called the F ratio. This F, can we generate F value? That's the kind of a discussion we are building up over here. Can I build up some kind of a, to talk about the p-value, to talk about the probability, I have to have a distribution. Can I draw the histogram for this guy? Can I draw the histogram? Can I draw the histogram for y bar? Yes. Can I draw the histogram for b naught? Yes. Can I draw the histogram for b1? Yes. In a similar way, can I draw that histogram for f? You look like you have one f over here, but that one f is not enough to get a clear idea about what's going on over here. As that we're gonna assume that someone else has done this experiment, and he might gonna end up with not the same f. He might gonna end up with a different f. See? Different f. So the variables f gonna change from person to person, but I have a f value based on my observed. See, this is called observed f value. Observed value. This is my observed mean square. This is my observed sum of square. What do you mean by observed? Because can I simulate them? Yes. Can I simulate sum of square? Yes. Can I simulate mean squares? Yes. Can I simulate f? Yes. Can I simulate 3? Yes. Can I simulate y bar? Yes. Can I simulate b naught? And b1, b1, 2, b1 through that 4. Yes. Yes, we can simulate anything. Like, see, we had that discussion like all the time. See, and remember that when we have something from the population, we're gonna say, see, we're gonna do first time, second time, m many times. See, can I do this one for based on first sample? See, they based on first sample. Can I calculate f? Sorry, I'm gonna go to the basic one for y bar from my data. Yes, see, y bar. Can I calculate b naught? Can I calculate bi? Bi stands for that all the b1s. Can I calculate PRE? Yes. Can I calculate R squared? This is pretty much same thing. Can I calculate for the first sample? Okay, first sample. It's a population. It's a sample. Then can I calculate mean square? Yes. Can I calculate mean regression? Use MS. I'm gonna stick to MS sum of squared, MSR. Sorry. MS mean squared. And can I calculate SS sum of squares? Sum of squares, SS. SS. So based on that particular sample, SS. Can I calculate F? Yes. Can I calculate P value? See? Yes. So that particular sample, based on that one, can we calculate P value? P value for what? If I'm going to calculate P value or any of these, we cannot because we have to randomize first. That part I'm going to take up. Okay. Can I calculate? Yeah, pretty much all these calculate. If you go to the second one, can you calculate all these again? Yes. That's why I'm going to call this on y bar 1, b naught 1, bi 1, pre1, r squared 1, ms1, ss1, f1. For the second one, you can calculate all this y bar 1, sorry, y bar 2, b naught 2, bi second one, pre, see, second one, r squared, see, that's the second one, see, then ms2, sum of squares 2, f2, like that, see, this is sample 1, this is sample 2, see, sample 1000 or something, sample m equals 1000, m. Can I go there? Can I y bar m, y bar 1000? Okay, I'm going to put m for my convenience. B naught m, bi m, pre m, r squared m, okay, mean squared m, sum of squared m, fm. That's it. Now you can see all these. In the middle, we have the observed value. In the middle, we have an observed value. See, observed sample. Observed sample. Based on the observed sample, you have all these. See, those are the one in ANOVA table. See, ANOVA table. The rest you cannot see. Most of them I'm talking about. Not only that, B naught, B1 you don't see in the ANOVA table. I'm talking about pre, R squared, MS, SS, and F, kind of like those things. These things you can see from another table. See, you can see. But that means that you can even generate if that if as like a distribution, you have to. That's how you get the p-value. P-values say that what are the probability of getting f values extreme than the observed f coming from here. And if it is related to b, p-value, you can say, you saw the p-value even has a b, see, p-value everywhere. That's the thing there, see, p-value here too, related to b naught, see, p-value related to, see, d naught, d1, d2, d3, d4. That's a one discussion. In addition to that, another P1, that's for that related to F. So what are the uses of these one? These one, if you want to check, run the test and see whether research will explain significantly the chance of admit for that testing of hypothesis, you really need these p-values. Those are called individual testing of hypothesis. You're going to do one at a time. See, you're going to check B naught whether it is significant, CGPA significant, LOR significant, SOP significant, separately one at a time. Or overall, you can take into account all these and then check whether they are significant or not. That discussion for that kind of a testing, you really need this F value or its corresponding P value. See? Like that. So that's the purpose of that having this P value. P value playing a heavy role at this stage now. Okay. So I have individual p-values. I have overall p-value over here. And again, see, again we have inside this one again that for that particular sequential ones, for that discussion, we have that one as well. See, these are sequential, hierarchical. See, we had that discussion, broad discussion last time. See, again p-value. But we mainly take into account this guy. And if this guy, that my observed F value, this is my P value related to that one. In this table, this is my observed D naught, observed D1, observed D2, observed D3, D4, and their corresponding P value. See? Or their T value. In that individual case, we use the T value or P value to run the test. In this one, the overall testing, you're going to use either p value or f value. So as of now, you have exposed to 3 types of distribution, actually 4, including normal distribution, okay, and the binomial. At a certain point, we talk about the binomial distribution, that when we flip a coin, and F distribution, see? F distribution, and BI, they have a distribution too. They are histogram too. Can you draw the histogram for this? Histogram for this one too. Yes, as you've seen over here, see, they are varying from sample to sample. That variation has to be taken into account. That's what we are doing in data analytics. That's why so many methods come into the picture. But within one method, you learn that one, that since this kind of a rigor, that's why they went into that different kind of a techniques later on. As I said, that same regression, rather than handling like this, they went to the decision tree. They went to the neural networks. See? And they went to the time series procedure, like that, another 3 procedures to replace this regression at the end of the day. But when you have a thesis or something, if you're going to present thesis, at the end of the day, you have to talk about all these 4 methods and compare, contrast, and see which one would be the best method to move forward in data analytics. In statistics, regression might be the best one because it has a rigor. But when it comes to machine learning, deep learning, and all kind of stuff with this the artificial intelligence, the neural networks play a very heavy role. But if you remember that you are tackling the same thing, decision tree, it's might be easy. Okay. So what I'm trying to say, this one, this is a little bit. See, this is what I'm talking about. Individual testing. Individual testing means H0, I can say. I'm not interested in B0, okay? Mainly I'm interested in B1 equals 0 versus HA, B1 not equal to 0. Okay? H0, B2 equals to 0 versus HA, B2 not equal to 0. H0, B3 equals 0. B2. B3, beta 3, sorry, beta 3, because we use the, they are beta 3 versus HA, beta 3 not equal to 0. H0, beta 4 equals 0 versus HA, beta 4 not equal to 0. All these can be easily represented like this way. H0 BI equal to 0 versus HA BI not equal to 0. You can say like that. So for each one, you use their corresponding p-value. See, P1, you can use the P1, you can use the P2, you can use their corresponding P3, P4 to make a decision. By looking at the p-value, you're going to say P is extremely small, or you reject H0. Or P1 value is compared with the 0.05, which is the level of significance, and make the decision. So individually, you can make the decision. See? So here that can be decided by, they were already given. You don't have to do anything by hand. Everything over here in this printout. All the PIs are given. See, PIs are given. So if it is extremely small, you're going to say that reject H0. H0 reject means that your intercept is not playing a role. Then research whether it significantly contribute to that one. You reject H0. H0 say that it is not. See, you reject H0. You accept this one. Accept means it's never going to be 0. That means beta 1 not 0 means like a research is explaining the variation in the chance of admit. That it's a good factor. As of now, we don't know it's going to heavily significantly that contribute to that one, because you have to use the other technique to verify and then come up with the best model at the end of the day. But anyhow, in this intermediate stages, at least that you know that you can reject H0 by looking at the p-value. The other one called the overall testing. What that means? Overall testing, you're going to take into account all these together. See, I'm going to set up H naught, beta 1 equals to beta 2 equals to beta 3 equals to beta 4 equal to 0. It's not individual. It's not one at a time. This is called one at a time. See, beta 3, beta 4 equals 0. See, not equal sign. There's no such thing. You're going to say at least one of the beta i's not equal to 0. At least one of them. See? We don't know which one. We don't know which one. That's why you later on go to the multiple comparison. Like so many things involved later on. But at this stage, that primarily you get this done with the aid of what? With the aid of p-value related to F distribution. F related to F distribution. I'm talking about this one. If you want to do this testing, this p-value can be utilized. So by looking at this p-value in this ANOVA table, see, 0, extremely 0, so the extremely small. Therefore, you're gonna reject H naught. You reject H naught. You reject H naught. Means you're gonna accept that one. You're gonna say at least one of the BI is gonna be not gonna be 0. But we don't know which one is. The BIs means they are corresponding that variable. Okay, those we don't know whether research or CGPA or state of purpose or that letter of recommendation gonna contribute significantly to the chance of admit. We don't know if you do the overall testing. That's why individually do and come to conclusion and say they were good, but it's not good at either. Then you have to run the overall test too. It's not enough. So you keep doing so many tests, but we don't discuss that in this class. But related to F distribution, related to this guy, related to this one. What do you mean by related to? That means that it is coming from a distribution. What that distribution then? It is coming from something called the sampling distribution of F. See? Sampling distribution of F. See? This can be get it done by related to that the example given in the textbook, randomization, through the randomization. See? Let's see how to get this. See? If you need the sample of F, see? You go to the F value. This function will work. See, F value of that the tip experiment. Okay, tip versus condition. Okay, I'm gonna shuffle this one because the randomization condition data coming from tip experiment in the textbook. Okay, text experiment. You don't have to do bootstrapping here. See, rather than bootstrapping, I'm gonna shuffle this condition. Condition means like a whether that according to that, this one. Sorry. Based on this one that I'm going to show you, keeping experiment revisited. Okay. Whether they want to know that, see, the back in chapter 4, we learn about an experiment in which the researchers sought to figure out whether putting hand-drawn smiley faces on the back of the check would cause restaurant servers to receive high tips. Whether they, by drawing that the smiley faces at the back of the check, whether they're gonna receive that higher tips or not. For that experiment, condition means whether they have a smiley face or not. See, smiley face, they don't put the smiley face, is control group. See, in a certain control group, they don't put, it's called the control group. This is called the treatment group. In a treatment group, they have, okay, you can, when you set up an experiment, one does not receive the treatment. Treatment means what you are interested in. So they say that they don't put the smiley faces on the back of their check. So even with that one, they are see, you're still getting tips. See? And then whether putting this one, see some extremes, see? More tips. So that kind of a comparison and contrast they're doing over here. So the condition, they call this variable condition, the other one is tip. See? So they draw the histogram for the tip. See? From the tip experiment, they saw that one. So see? They got the favorite statistics for the two groups. There are two groups, control group and smiley face group. Without smiley face, this one with the smiley face. See? Look at the averages. See? Average is 33. See? When you have a smiley faces, that see? On average, they are making $33.04 or 5 cents. See? This one. But if you go individually, that's a different thing. Individually, we didn't take into account anything. We go overall everything and see that experiment I'm talking about. See, either this way to smiley faces, control. Control means no, this one. See? Here, so the mean difference, you can remember the means are here. You can draw this one. See? So, see? Then see, P and F ratio, you're going to revisit it related to that one. See, tip experiment. See, that's what they are trying to do. You can easily get that one by that setting that one. See, tip versus this one. You know how to get that one. See, LM tip convenience, this one. Okay. And later on, that see, you run this one. Look at the condition model. Let's say that this model run one more time. See, you get the see. Intercept conditions. My condition is the variable. It's gonna go from. There are two groups. One group is control group. This other one is smiley group. From the control group to smiley face, that gap is $6. See 27. That's all. See. So see, if you want a supernova, you know how to get the supernova. Put the supernova of condition model. See. Like that. Okay. But what we are trying to say over here, for related to that one, you're gonna see in here this F. See this F. See this F. This F is based on you have observed whatever that one time you have done this experiment based on that data only, as I mentioned over here. See, based on that. See, based on this observed sample only. So I want to make sure that how we got the p-value related to this one. P-value and even for the pre, can you do that one? Yes. Can I draw histogram for this one? Yes. That's how we're gonna build this up. See, F value, if you set this up from the data, the tip experiment, go to condition, I'm gonna shuffle the condition. Rather than that particularly predetermine, okay, these table would have the smiley faces at the back of the check. These table do not have. Rather than you predetermine and pre-set up that one, you're gonna shuffle everything. That's another way to generate the data, like a sampling, the bootstrapping or simulation. There's a third method called the randomization. See, first method bootstrapping, pre-sampling. Second method, simulation. Third method, randomization. You can randomize. See? There's no data being that generated through like a R norm or that resample. See, you don't have that. It's being done through this by shuffling this the condition. Another way to get this done. See? So from that one, can I? That's only one. Can I build up a see? Can I build up a so many F values for this one? Yes, if you redo this one so many times, I can do that one. I can build up the so many F values. Sampling, distribution of F, see, is what? Do 1,000 times, see? 2000 times, same thing. F value. F value means it's gonna, F value is a function. F value, same thing, okay? People, shuffle, condition being shuffle. You put the data. That's it. No resampling, no simulation. This is randomization. Third method, tip experiment. Okay. What is your variable? This is my variable. This is my data frame. This is data now. See how many data being generated? This one. Once you draw the histogram, like that in Viber, this time we're going to have a different kind of a distribution. Look at these are F value, F value, F value. Okay, I'm going to call that one, not F value, F value, yeah, sorry, not F value, yeah. That distribution would be like this. Skew to the right, if you smooth like that. See? This is the frequency. You can draw the histogram for that one. Frequency, it looks like this. Having a thick or thin tail. See, like that. See, not this one. So the shape of this one, shape of this distribution, see, shape of the F distribution. This is called F distribution. Is decided by degrees of freedom of regression and degrees of freedom of error. In a normal distribution, shape is decided by mean and standard deviation. Here, this is decided by degrees of freedom of regression and degrees of this one. Okay. So those are the parameters of the F distribution in another way. See. So I'm gonna go ahead and then locate my observed value. See, observed F. See, F naught somewhere here. F naught. See, observed F. So sample F. See. That's in our this is related. This is a different example. In the homework example, this I'm talking about this value. You locate this value somewhere. 364.798. Let's say that 364.798. Then I'm looking for area to the right of that one. F values extreme than the observed F are called the P value. That's how the P value comes into the picture. So this distribution, P value is nothing but probability that F value extreme than F naught. Another way we're gonna write this one. We're gonna write here. P value is P value. I'm gonna say P value is nothing but probability F greater than or equals to F naught. Not F val. F value. Probability. That's how you get the P value. That's how you got the zero. In this case, it's nothing. See? Zero. But it is same as it is look like a, you got the F value. How do you get the F value? By dividing 0.386. Sorry, dividing 0.986 divided by this one. That's a different story. But how do you get the P value? P value based on the distribution. That's what I want to emphasize over here. F naught you can get. This F naught F naught you get from mean squared regression divided by mean squared error from ANOVA table. Even F as a like that kind of a distribution. But F means that if we use the F for that, it has been named after Fisher, who is considered to be the father of modern statistics. And it should be actually Fisher and Snyder, both, that they contributed equally to that, come up with this one. On the other hand, can I get this done using the bootstrapping? This is randomization. Can I get this done using the bootstrapping? Let's say second method, bootstrap. Okay? Bootstrapping rather than that. Yes, we still can. Then I can say boot sampling distribution of F. I'm gonna distinguish this one from the other one by telling this one's random one. Rand. Okay, I'm gonna put rand over here. Rand sampling distribution of F. Yes, by the randomization. This one through the bootstrapping. You know how to do that one. 2000. Okay, times F value between what one and what tip tilde. Condition we're not gonna reshuffle this one. That's in randomization. Now I'm gonna generate data. Data, how do you generate? You go to resample. You see, you go to resample, go to tip experiment, same thing, and you say you have 44 entries. Those entries will be recycled. You're gonna utilize again and again and again. How many times? 1,000 times. You can bootstrap that one as well. And from that one, can you draw histogram? Yes. You can draw histogram. Again, as well, this one. And again, if you do that one, you're going to have that similar kind of like a right skewed distribution. Right skewed, or we're going to say positive skewed, positively skewed or positive skewed, something like that. Distribution. F distribution, this one F distribution, this one frequency F frequency, say frequency coming F, this one F value. See? From that one again, you can do the same thing. P value is nothing but P value is nothing but you have F naught. So this area to the right is P value. P value is nothing but probability F val greater than or equals to F naught. Same thing. Now, how do you get this one in that you're how do you get this one, this distribution that sorry. Let's say that in that experiment, I'm going to go back to this one, and F naught has been given sample F 3.305, okay? 3.305, this one, okay? So this one, 3.305 in that experiment, okay? By running that, I think I'm going to have a look at it one more time. Yeah, see, 3.305 observed value. This is the tip experiment, okay? Experiment. 3.305. So how do you get this done in R? What are you going to do? That if you have a tally, you can use tally. Okay, to calculate p value. See, if you go to p value, you're going to go to tally. Okay, I'm going to go here. Tally in R. Okay, tally. You go to f val. Okay, greater than or equals to, you can say 3.305, comma, data is nothing but sampling, okay, rand sampling distribution of f. See, that will give you the true area and the true and area to the right and area to the left. You can remember. See, you're gonna see this is a variable. See, that variable greater than or equals to observed value. Okay, and data is random sampling distribution of f. And this one you can do the same thing with the bootstrap one too. Bootstrap one you can do the same thing. Okay, you go over there in R. Okay. You're gonna set tally f var greater than or equal. If you want, you can call this one sample list. Sample list. See, sample list. See, sample list. See, some data is nothing but boot sampling distribution of it, and that will give you true part and false part, true and false. True value. Under that one, true means this greater than one, the other one is less than. So that area you can see here. Okay, the answer you can get on that. That's the way how you can get it done. In addition to that one, what they did was that we have that mathematical one. The mathematical one. Third one is mathematically they develop F distribution. Mathematical one. See, it is decided. See, it's already done. It's very precise. See, this distribution has been already built up. See, mathematical one. It's based on what? Degrees of numerator. I'm gonna say num is same as the degrees of freedom of regression. In that particular case, 42. Okay, degrees of freedom. One. I'm sorry. One. Number of regressive variable is one. So degrees of freedom of denominator, which is degrees of freedom of error, which is n minus 2, and it's going to be 42. This is number of regressive variables. Mathematically, you can do this one. And then you go over here and then you locate that your F naught. F naught is nothing but 3.305. You call that one sample F. See, you save the sample F. See? And I'm looking for this one. This area. You don't have to use the tally this time. You can use what? P-value. Get the P-value. P-value is nothing but probability. F, this is F, okay? This time we call F greater than or equals to F naught. That one you can easily get. I'm going to write this way. Look at this way. 1 minus probability of F, okay? PF. Then you're going to give what? Your observed value, okay? F naught, which is sample F. That's not enough. You have to give what? Degrees of freedom of regression, numerator, which is 1. You have to give, this is, if you want, you can say 3.305. Somehow, okay. That will give you the answer. Which is 1 degrees of freedom of denominator, which is 42. See? Why I did 1 minus probability? Because the program will get the area, this part will calculate the area of this one, area to the left of that one. That's why I subtracted from 1 to get the area to the right. Your area to the right. This one is area to the right. See, I need the area to, I need the probability that F value extreme than observed value. That's called the P value. The will that R calculate that one? No, he's going to calculate the area to the left. That's why I subtracted from 1. 1 PF, that's the code, and the sample F, you have to give the quantile, which is 3.3. You don't have to write that 3.305. Then you say sample F, if you go and read that one. And if you assign to DF num, then it's going to read this one, which is 1, DF denominator, which is 42, close it. That's mathematically you get it. See, these are approximate values. These are mathematical values. See, P value. So here P value has been calculated through 3 ways: using the randomized F distribution, using the bootstrap F distribution, using the mathematical F distribution. Now you might be thinking, do we have a mathematical distribution for y bar? Yes, that's normal distribution. Can you remember? Do we have a mathematical distribution for B1? No. Can I make it approximate to normal? Yes. Yes. But they haven't come up with any fixed distribution like this. This is F distribution. That's how you can do that. That's something that I want to bring to your notice at this stage. Can you do the same discussion for the pre? Yes. Yes. Would that the pre would be in the same setup? Okay, similar, pre and F will show you the same kind of a distribution. Same. If you do that one in this setting, instead of here, you can change this one to, okay, if I use a different color. So instead of F var, if you use the pre, okay, can I use the pre here? See, that will give you what? Sample of pre. See? That means rand sampling distribution of pre. See, like that for the same thing. Okay. Then instead of F, you have a pre. That's what I want. I do not write too much over there to mess up that one. Same thing over here. You can say P. Then you have a boot sampling distribution of pre. Can I draw the histogram for that one? Yes. Then you have a pre here. Okay. Pre here. Here, pre. See? But we work with the observed value. That's a different story. You see that that is getting rigorous like that way. Whatever we observed is not the correct one. There are many if values existing in the system. If that had been done by different people, that's variation is the one we are trying to tackle over here. See, extreme, then if not this one. Then if not, yeah, well, you can do that now. It will have a same kind of a distribution instead of F kind of a, you can say that one sampling distribution of F. Okay, that one you can say sampling distribution of F. Go back to that color and make it right over here. Sampling distribution, sorry, sampling distribution of pre. Not, we don't call that distribution, we call sampling distribution. That's one. Okay. Sampling distribution of pre. For the pre, we don't have a mathematical distribution. They have built up. But if they have the two people who invented that particular distribution, Fisher and Snyder. Ronald Fisher and Snyder. Okay. So that's that one I should bring to your notice at this stage. So see, that's how the p-value comes into the picture. Okay. So example of those with the research experience, again that we tend to have a higher chance of admit than those who do not have same as in assignment. Increase their chance of admit tends to increase. The better the LOR, the higher the chance of admit. The better the SOP, the higher the chance of admit. Intercept. Intercept is the chance of admit to someone who has no research. LOR 3, SOP 3, and GPA 8.6 based on whether you are using centering one or not. If you use the centering, I did the centering without centering in two ways. Whatever you are using, when I was centering this one to get rid of the negative value from that intercept, I just subtract 8.6. Just subtract 3 only. Later on, I just did the same thing by subtracting just exactly the mean. Mean is 8.5989. Here 3.4525, 3.43. Like that. So if you want, you can build up that discussion like that. Anyway, any number. But then if you put that negative value, you have to make sure you're gonna say, sorry, chance of admit for someone who has no research, but LOR should be 0. This should be 0. This also should be 0 if you use the negative value. Okay, negative value. Okay, I'm gonna go back one more time over here. Okay, if you have a negative value after you that without doing anything, see. Why they get okay, sorry. See, negative value. If you use the B naught for this one, then you're gonna say that the definition is, but sorry, here. See, this is they were asking how we can be, but this we call the chance of admit with the research 0, CGPA 0, LOR 0, and SOP 0. Okay. Let's say regression coefficient. Okay. You can define that one. So this one, when you're gonna regression coefficient for the centered model, for every 1 unit increase in GPA, see, controlling for other variables in the model one at a time. Okay, I'm gonna control other variables. The predicted chance of admit increased by 0.169. I'm here. 0.169. I'm controlling one at a time. I'm gonna get the B1 slope with respect to that particular variable only. See, for every 1 unit increase in GPA, controlling for other variables in the model, the predicted chance of admit increased by 0.16. For every 1 unit increase in GPA, for an average person who does not have a research experience and a scores, the LOR and SOP equal to 3, their predicted chance of admit increased by 0.169. Because it's based on centering, after centering. Even after centering, you can talk about that. Huh? See? For every 1 unit increase in GPA for an average person who does not have a research experience and who scores a LOR and SOP equal to 3. The predicted chance of admit increase by 160. Same way, see, the other variable. 2 ways we can explain that. Okay. The other one, 2 ways. LOR, SOP, 2 ways. LOR, 2 ways. GPA, 2 ways. Research one we don't take it into account because the research one we're gonna see, because the research is we research already in that one, but we're gonna control that one. Or you can simply say you don't have to control. You say it doesn't have a research. See? First way how you can talk about that LOR, assuming that LOR is quantitative. Or when the second way of explaining that one, say increasing the scale of error for average person who doesn't have a research. You have to make sure research part will be 0. not have a research. It does not have a research. CGPA and SOP equal to 8.6 and 3 respectively. Their predicted chance of admit increased by this one because these are after centering. This is before centering. After centering, we by subtracting. I did center in 2 ways. If you want, you can go to the another method too. Third method. See, third method and say that with respect to this one, mean. See, then you can say something like that. Sorry, for every 1 unit increase in scores of SOR for an average person who does not have a research experience, and CGP and LOR equal to their averages. When they are equal to their average respectively, their predictive chance of admit increase by that one. That's a third way of explaining that. Instead of 8.6, that's the amount that I have subtracted from each and every data entry from the CGP. See, this is the amount that I have taken amount. This is lower. See, for each and every one, CGPA, LOR, SOP, I explained that one. See, but those are quantitative. You know the quantitative versus quantitative. When you have to explain in one way, then for the research you can explain different ways. See, regression coefficient for the for every 1 unit increase that one. CGPA, LOR, SOP only. The other one, assuming that it's a categorical. When categorical, how do you explain? You know how to do that, and we explain. See, that's the average. See, then we get the reduced model. Now you guys see, SOP does not contribute to the model according to the p-value, F ratio, or pre. See, 3 of them you can take into the. I'm talking about here SOP. See, look at the. Hold on here. See, greater than 0.05. So we do not reject H0. We do not reject H0 means, let's say that one is our beta 4 individual. See, beta 4. See, we do not reject H0. That means beta 4 is 0. Because we do not reject by looking at P4. P4 is 0.75. 0.75 is greater than, see, this one. So we do not reject H0. We do not reject H0. So if mainly we go to the this question, keep going down, multiple regression, those are they contribute. And they say that the fit a reduced model, okay, we can say that things what, let me see. Number 3. So, number 3, you can say things P4, which is 0.75. See, 0.75, 31. For statement of purpose is greater than alpha. This is alpha, okay? Alpha means level of significance. Which is 0.05. Level of significance 0.05. It's a complement of the level of confidence, okay? Level of confidence is a complement of the level of confidence, which is called 1 minus alpha is 0.95. . confidence 1 minus alpha is 0.95. We do not reject H naught beta 4 equals C. We do not reject. That means beta 4 is 0. That implies statement of purpose does not contribute significantly to the variation of chance of admit. Chance of admit. Do not reject means another way we can say the test is not significant. If you reject, we're gonna say it's significant. See, that's why you're gonna go to then now you drop that one. Now you're gonna get that. Therefore, you can drop that one. You can say chance of admit. Now you can set up with beta naught, beta 1, beta 1. What's the first variable? You put the CGP, LOR, research first, no? Research, time research. Keep the same order. Easy. Research, beta T, CGPA plus beta 3, letter of recommendation. The other p values you already check. Okay, you might be thinking what happened to other p values. See, all the other p values extremely small, low, less than 0.05. Why we are using 0.05? That's a level of significance we have considered as this level. Because if you want, you can go to 0.10, but doesn't matter. By convention, we go to this one. So this one is y equals now beta naught, beta 1, x1 plus beta 2, x2 plus beta 3, x3 plus e. This is called the reduced model. The reduced model. Reduced model. Reduce. You reduce some variable. They were unnecessarily that involved with this one, and it costs a lot. See, you have to take it out. See? Reduce model. See? The other one is called the full model. Full model is the one that we play with earlier. See, y equals beta naught plus beta OB, doesn't matter. Beta OB, okay, I wrote the beta naught, beta 1, x1, beta 2, x2 plus beta 3, 3 plus beta 4, x4 plus epsilon. Actually, if you write the beta, you write the epsilon. Doesn't matter. Or with the B0, B1, B2, that's the same thing, okay? This is some population version that one. Okay? So that's why they were asking now, whatever you have taken out with that taken out one, see, we have taken that down. See, now now we're gonna run. See, LORC. What is LORC? Why it doesn't? LORC. CGP research without centering. LOR, I didn't center. Okay. Let's say without centering. Okay. If you want, you can go with the with centering too. Okay. See, without center, I'm gonna do this one without centering, with centering. Okay. So without centering, reduce model. See, without centering, reduced model, supernova and all kind of stuff you can see summary and kind of stuff. And center in one, they say they don't have LORC. See, let's see that. Let's do the centering here. This you prefer to subtract mean. Even the centering you can do in two ways. Subtracting a certain number or subtracting their own mean. So now let's see how it goes. See, like that. Then what they were asking for us to do. Okay. Then you can put all their see, same like earlier. Okay. These are for the pre again. I want to tell you this one same as for the model. Okay. Pre when you run supernova again. See, supernova again. See, I'm talking about this one in reduced model. I'm talking about this line. So this should be for the model same like last time we did. See, I can see that I can copy and paste that one here. Um, Take this out. Yes, stop. No. Okay, another one. Go there. So this is for the model. Okay, model again, same like the way that we had here. Okay, that's what I want to tell you. Same thing. Just try that one at a time. Okay, just it's messy enough. I don't know how to do anything. Okay. So you know the same thing without that this guy. Okay, you don't have to worry about this one because the letter of statement of purpose we this time we didn't include it. Which model is best? The first model with explanatory variables or the reduced model with only those that contribute to the model? Let's see what is that. See, which model is the best model? Okay, the pre for the full model went from 0.7872 in Q1 to 0.7869 for the reduced model in Q4. The F ratio went from this one to this one. The F ratio increased because it is based on the number of degrees of freedom, Q1 and Q2. The pre did not change much because the removed variable SOP did not explain much variation in chance of error. The reduced model is better because it is parsimonious and explain the most variation with the fewest parameters. It is less complex. When comparing two models that explain similar variation, the simplest model is favored. See, you always gonna go with that one, but at the same time you have to compare and contrast that that pre-value. See, pre-value has gone from 0.7870 to 0.7869. See, not the drastic changes. Because that the reason was that even the SOP taken out, even earlier, it says that very clearly this guy has not contributed at all. See? That's why even if they were taken out, it stays the same. See, not any changes. The full model went from 0.7870 to 7869. Pretty much the same. In Q4, this is in Q1, this is in Q4. The F ratio went from 664 to 487. See, better. Because now you are using what? F ratio increased because it is based on the number of degrees of freedom. See, in question 1, we have degrees of freedom 4.4,395. In question not 2, it should be 4. 4 we have degrees of freedom 3 and 396. See, I'm talking about numerator and denominator for f. 4 and 395. Why 4? Why 4? Why 395? See, 4 is number of regressive variables. How many regressive variables in the full model? 1, 2, 3, 4. How many regressive variable in the reduced model? 1, 2, 3. That's the number for the regression. Degrees of freedom is nothing but number of regressors. So full model 4, this one, this one. How about that, this one? N minus P. N is number of sample size, which is 400, minus P stand for number of parameters to be estimated. How many parameters in the this one? 1, 2, 3, 4, 5. 400 minus 5, 395 in the beginning, full model. And later on, how many variables we have? Look at how many variables, sorry, how many parameters to be estimate? Data 1, data 1, data 2, data 3, 4. 400 minus 4, which is 396. So it is based on the degrees of freedom. Now the degrees of freedom, see, change. See, look at 4 to 3, 395 to 396. That will affect to the increment of that f. See, f has gone up 486. The pre did not change much because of the removal variable, so did not explain much variation. The reduced model is better because it's parsimonious and explain the most variation within the fewest parameters. It is less complex. Because of that, we're going to take into account the reduced model. Okay, because of that reason. F is high, not the pre. Pre cannot be even taken into account. But the pre-high, pre will be affected by the degrees of freedom. Degrees of freedom are determined by the number of regressive variables and number of parameters to be estimated. When you something unnecessary one taken out, it will affect to the f variable. F variable is already determined by degrees of freedom. As I said, that f distribution is completely determined by the degrees of freedom in regression and in error. Okay, that's why. Okay, now good. So how many parameters are in the multiple regression model in Q1? That reduced model in Q3, reduced one, I'm sorry. This one, I think I want a little bit change here. It's not Q. It's not going from Q1 to, sorry, in the Q1, it's not to Q1 to Q3, this one, not Q4. The F ratio went from this one in Q1 to what's the one in Q3, and the F ratio in Q3. We are working on the fourth question right now. Okay. This one. Someone. Yes. This is okay. Okay, good. Yeah. See, and 5. And we can ask you question 5 and question 6. Okay. They both together. Let me see if I did right. Okay. Q5 and 6. How many parameters in the reduction? Both together. Okay. 5 and 6 both together. In Q1 parameters, how much? Q1 means in the full model. Okay. Full model. Full model. Full model. Q1 means full model. And 5 parameters, Q2. No, not Q2. This will be Q3. Reduce model. 4. Then 7. 5, 6, 7. How did the parameter estimate change as a result of removing explanatory variable? Why do you believe this occurred? How did the parameter estimate changes? Parameter estimate changes, no? Can you remember? Parameter estimate means this one, see? This one changes. See? This value is not the same value. See? In the full model, see? Sorry, the full model. Come on. Yes, the full model 35,735 research. Is that the same thing? Parameter estimate. The change. This one, sorry. This is 70. See, this one, intercept. The slope stays this one in LORC, that's the same. This is LORC, that should be the same, but I'm looking for the full model. Full model, see, 355. Research. Now, 357. Earlier, see, 16, 20 or 21. This one, see, 17 or 22, like that. This slightly different. Without centering or not centering, like that, see. But then without or with centering, the slope's not gonna change. We know that one. But slope's gonna change by removing variable. Okay, removing variable. See, the parameter estimate for the other parameter did not change very much. See, did not very much, but they kind of see. This happens because the variable that was removed was not contributing to the model. See, because they stay the kind of a same, not drastic change. See, in the full model, if you have a 355 point or 355, that's what I meant. Here point or 355 still 357. See? They were not drastically changed because they stays the kind of a same, because that other variable did not explain that much, explain variation of the explain much variation in chance of, see, chance of admit. Okay, chance of admit, variation chance of admit. Of admit. Because of that reason, it did not contribute. We, for the sake of putting that variable into that system, but we didn't know in the beginning. Later on, we have to figure out whether which one is contributing well or not. And later on, we remove it. See, it's an elimination process. Okay, elimination process. Okay, like that. That's the reason. Then Q8. How did your interpretation changes as a result of removing experimental data? Why did you believe this occurred? Okay. See, the interpretation change for the intercept, because it is now the predicted change of admit for someone with no research experience, the GPA of 8.6, assuming that 8.6 been subtracted in centering. Okay, LOR of 3 instead of the predicted chance of admit for someone with no research experience, GPA 8.1. See, and this is SOP3, not over there. That's what we are trying to say. Now it is not dependent on the value of SOP because it is not in the model. That's the reason. I'm gonna ask that. How did the interpretation also change? Interpretation change because the SOP not there. Simply SOP. Earlier we say SOP also 3. Now we don't have to say that one because it's not in the model. And this one, let's do this one little bit do, and then we can stop because I have to get into the other class. We can finish everything tomorrow. Extra, okay. See, extra credit 1. What is the predicted chance of admit for respondent 234 using the multiple regression full model from Q1? Chance of admit, multiple regression model from Q1 is easy. The predict if you put the, see, that's, you can get this done in survey. See, summary, see, multiple. The centered one, I'm using the centered one. Okay, using centered one. Is the, okay, good. So maybe model 1 center. Let me go over there. Model 1 center. Let's see that. Model 1, 2. Which model I'm using? Model 1 center. Okay. Model 1 center. Model 1 center. Okay, model 1 center. No, model 1 center. Okay, that's the one I'm using here. You can use any model that you want, model or model. Not, yeah, I think that's the one. Yeah, good. Enter. See, I'm gonna go ahead and see. Include, see, prediction. Go to the model centered one, go to the coefficient. See, I'm gonna get the coefficients. See, look at the coefficient times, see, intercept, see, and plus the research, and times the that go to the data 234 persons research results. Go to the dat, comma, research, and say it will extract the value for that research for the 234 person. Talking about this one, 234 means here 235th one. Recently, no? So that the top one I used for that. So the heading. So they were asking about 234th one. Yeah, say 34th means 35th in this Excel sheet. So what are the? Just get the GRE, TOEFL, university, blah blah blah. Research yes or no. See. These values will be extracted and will be multiplied by the coefficients. That's what we are doing. See? Intercept, you got the intercept plus go to the model centered one, go to the coefficient. From the coefficient, I need the coefficient of research coefficient. See, double bracket, see, research plus. First, you get the data, see, 334. See, it's entry you can pull out. See, 234, blah, blah, blah. This will be given over here. That what I'm trying to say that I'm plugging into this one. Data node, data 1, x1 for 234th person, x1. Okay. Research for the 234th person. Okay. So I'm looking for predicted value. See, y hat for chance of admit for 234th person. Data node. See, B node. I'm gonna write B node for the 234th person plus B1 for the 234th person times. No, I'm not doing the right thing. This one stays the same. You don't have to change. B naught, sorry, B naught stays the same plus B1 times X. X means like let's say that what is X1? X1 would be research, you see, research of the 234th person. Research 234th person. And B2 plus CGPA of 34th person. B3 of letter of recommendation 234th person. B4 of statement of purpose of the 234th person. You don't put the error because you are estimated value with the hat. See? Estimated chance of admit for the 234th student. Admit to the 234th student. That's what we are trying to calculate this in different ways. And then it's going to call the prediction for that person. 0.61, but his chance of admit is how much? Chance of admit 0.64. See, if the predicted value is 61, what's the difference? Difference is called the error. See, difference is called the error. We got 0.61. Let's say 0.61. This one equals 0.61. See? 61. But y for 234 is how much? Chance of admit they predicted. Not the predicted value, not based on the model. Earlier he has a chance of admit of this much. 0.64. 0.64. See? 0.64. So the error should be what? The gap of these two error. To put this one y 234 minus y hat of 234. Which is 0.64 minus 0.61. 0.23. Error for 234th person. And that. Now you can find the error. See? Another way of doing that one, see? Prediction. See? 1 by 1, 2, 1, see? 3, 1, 4, 1, see? 5, 1. The models, see? This is the data. See? Go to the research terms, model centered. Go to the coefficient. If you go to the coefficient, you can read, see? Second one, see? First entry. See? Second, see? Second row, first column, third row, first column, like this. See? Fourth row, first column, fifth row, first column. From the coefficient, I'm talking about here, extracting from here. See? Extracting from here, first column. See? Second row. See? Second row, first column. Second row, first column. See? We are extracting. Third row, first column. Fourth row, first column. Fifth row, first column. Another way to get this now. See? Rather than put the name. See? Prediction. Same thing. Another way rather than that one, see, go to coef and then you read from there. Read from there. Go to there and read. Same thing. Oh, because my coef not working because we had the same issue with the B not D1 and pre and F. Okay, I had to go to sandbox and run. You can do like this way too. Okay, or just simply see Q1 make function of that one. See another way to do this one. See, you get the model and make a function. See any way you want. See, till you get that one. And if you want the true chance of admit, which one, see, you can pull that out too, see, 0.64. See, predicted chance of admit, see, 0.61, see, pull out from that one, residual, see, like that. So you, in the similar fashion, you can do the same thing for residual. We asked for the residual for the 28%, 128% in the second one, see, residual only. here we don't ask the residual, we have the y hat. You do the similar setup. Okay, similar setup for this one. See, if you use this part for the one shot, you go to the 128 chance of admit. See, from the data, and the q1 is the making function. For the function, you're gonna put all these. See, their values. See, put the values for the function. See, that will calculate the estimated value one shot. Here I'm showing you that so many method way to get the prediction up to here. See, for all of them. But if you're gonna narrow down that one to the not all of them, sorry, the 234th person, and then see later on you get those values and then get the residual. The same method you can use over here. This residual is 0.05. This residual is 0.02 or 0.03 as I calculate. Okay. That's all you have to do. So get a clear idea what's going on. Then later on they have another one, something that I will show you. They're going to talk about the reduced model minus this one, and then they built up F2. You can build the F2. You can learn those things down the road. Reduced model and full model, that one divided by the full model called the F distribution again. F, if you want to calculate F to see that which model would be the best model, you can go, you're going to do the partial F. It's called the partial F. Partial F. It's a full F. This here we have the F. We did everything based on F. That you get the P based on F. But later on we can talk about the partial F as well. So many things that will be added one by one. And on the other hand, as I said in the very beginning, this everything can be get it done using this is Titanic example I had for the decision tree. This is neural networks, and the same thing get it done using different frameworks. Neural network framework, decision tree framework, time series framework, or regression framework. So if you can learn all these four, that's going to be very useful down the road, and then do a very the best job at the end of the day. Okay, but we should just barely that touch this regression little bit here at this stage, because you're going to learn all this stuff in large scale later on. Okay. So I'm gonna go ahead and stop over here. That do you guys have any questions? If not, I'm gonna let you go. That see you guys tomorrow. Stay safe, be well, and then have a good night. Okay. See you guys tomorrow. Take care. Tomorrow will be our last day. Okay. Take care. Thank you. Have a good night. Yeah. Thank you. Take care. Okay. I'm gonna go ahead and explain this one in detail tomorrow. Okay. Okay. Have a good night. Take care. Okay. I'm gonna stop here.